The third talk is from Professor Rustom Antia, and Rustom Antia is going to be talking about immunological measures, or about how immunological measures of protection determine SARS-CoV-2 transmission and COVID-19 disease. So we have the slides there now, so I'm going to hand straight over to Rustom. So thanks very much for giving a talk. And again, I'll sort of interject after 15 minutes to say there's a minute or two left.
Okay, so what I'll be talking about is how the immunological parameters in immune hosts who got infected, affect the transition from an epidemic to an endemicity. So really, as an outline, what we're doing is we're taking a sort of cross-scale look at an epidemic. Typically, an epidemic is viewed by epidemiologists as sort of transmission of an infection in a population of hosts. And typically what happens is one considers susceptible hosts getting infected, and after getting infected, they become immune. And most of our models typically assume that immune hosts are sort of perfectly immune. They're sort of completely refractory to getting infected. And what we're going to do, because it seems to be relevant for coronaviruses, is that immunity isn't perfect. Two things happen. Immunity wanes over time. And the second is immunity, as it wanes, doesn't allow an individual to return completely to the susceptible state, but is in a partially immune state. So really, we're going to integrate a little bit of immunology, which is what happens when you have different amounts of immunity in a host to the dynamics of infection, and see the consequences of that for the epidemiology of spread of an infection and the level of pathology you expect to see in cases. And to do this, we sort of take some lessons from some work that was first done by Beth Halloran and her colleagues, who looked at how the level of immunity, or in the case of vaccines, can protect in different ways. So really, this is taken from the work of Beth Halloran, who did this, who introduced these concepts for vaccine efficacy. And what we're just generalizing them to is efficacy with different levels of immunity. So the immunity of an individual can provide protection in three ways. The first is it can reduce the susceptibility of the individual to getting infected. So that is called IES. IE is for immune efficacy, and the subscript S is reducing the susceptibility of the individual to getting infected. If the individual does become infected, having immunity prior to the infection can help in two ways. The first is it can reduce the pathology the individual has. So pathology has a number of definitions, but one of the ones which is relatively straightforward to measure is the probability of death given infection. So if you're immune and you get infected, you have a lower probability of dying than if you're susceptible and you get infected. And finally, if an immune individual gets infected, the individual can transmit less. So having immunity at the beginning can change the amount of that individual transmits in the population. Now, most of the classic studies in epidemiology, and very beautiful studies, consider infections like measles. And measles really provides lifelong protection from subsequent infections. So it's really a very simple and very nice infection to model, because really, if a person gets infected by measles, the efficacy of the individual's immune system prevents the person getting infected. So immune individuals reduce the spread of infections in the population. You can have very nice analysis of long-term herd immunity being generated. And if you vaccinate people early enough, you can even think of eradicating the disease. So really, how do we know this for measles? And there's a beautiful history of our understanding of measles infections. And something that's particularly elegant is early work done by the Danish physician Parnum, who studied what happened for measles when there were epidemics in the Faroe Islands. So back in the 1700s and the early 1800s, the Faroe Islands were a relatively isolated population of over here, and they were visited occasionally by ships. And occasionally, one of the travelers on the ships would bring an infection to the island, and the infection could sweep through the inhabitants of the island. And what Parnum did was he observed the consequences of measles epidemics, and there were two measles epidemics in particular, one in 1781, which went through the population and infected virtually everyone. And then for over 60 years, there was no measles on the island. And then the second epidemic happened in 1846, more than 60 years later. And Parnum documented that during the 1846 epidemic, again, virtually everyone got infected. So over 99% of the susceptible individuals on the Faroe Islands got infected in the 1846 epidemic. But crucially, Parnum observed that none of the survivors of the 1781 epidemic, all of whom had presumably got infected in 1781, none of them got measles. So really what this suggested to Parnum was that people who got measles in 1781, they didn't keep spreading measles in the population because there was no documented cases of measles between 1781 and 1846, but that their immunity lasted for over 60 years and protected them from getting measles over 60 years later. So this was a wonderful example of long-term, very strong immunity, protective immunity. Okay, so now we come from measles to coronaviruses. And really an interesting place to start with human coronaviruses is to start by looking at what happens with the endemic human coronaviruses. So these are the four, and the two alpha coronaviruses and two beta coronaviruses, and these which are circulating in the human population. And it turns out that immunity to these coronaviruses is not lifelong, and we frequently get reinfected by these coronaviruses. So how do we know we get reinfected? There are a few really elegant studies which I'm going to sort of describe, which show we get reinfected. One way of looking for reinfection is to look for a boost in the antibody levels to that particular coronavirus. And so here in the right-hand panel is some work from Edridge et al. In Nature, which was published in Nature Medicine a year ago, where they show the antibody titers to 4 circulating human coronaviruses. So those are the 4 ones at the right. And the bottom is antibody titers to measles. So you can see the antibodies seem to wane gradually over time to coronaviruses. And every now and then they spike quite a lot. And a spike corresponds to getting infected with that particular coronavirus. And so you see that every few years, there's signs that people get infected with these coronaviruses. So really, this shows that immunity is not lifelong. Immunity wanes over time, antibody levels wane over time, and every few years, people get reinfected, and that boosts their immunity again. And you can see that, as might be expected, for measles down over here, the titer of antibodies to measles stays relatively constant. immunity to measles doesn't seem to wane over time, and people don't get reinfected. Okay. Another way of looking for reinfection is to directly look for virus in people by sampling them frequently to look if they have signs of infection by having virus in them. So really, there's a very elegant study, again, done last year from Jeff Shaman's lab. And over here, you can see in the right, they show the probability of getting infected for the 4 coronaviruses in these 4 small panels as a function of time after the beginning of the study. So you can see the study lasts for just under 2 years, and focusing on these 2 coronaviruses, OC43 and HKU1, on the x-axis is time after enrollment of the study, and on the y-axis is the probability of being infected. And you can see that after about a year, about half the population for OC43 and about a quarter of the population has shown signs they've had a new infection by direct measurement of virus in the individual. So really, another way of looking at whether people get reinfected by circulating human coronaviruses. A third way of looking at what's happening with circulating human coronaviruses is by looking at the antibodies in the individuals. And a study about 10 years ago looked at both the levels of IgM antibodies and IgG antibodies in the 4 coronaviruses as a function of age. So really, they looked at the 2 alpha coronaviruses, which is S229E and NL63, and the 2 beta coronaviruses, HKU1 and OC43. Now, IgM measurements, which are shown in purple, are a sign of recent infection. IgM only comes up on primary infections, and it wanes over a period of a few years, or a year or so. So really what they see is that IgM shows up in young children and then wanes over time. And this is a pattern which is seen in all the 4 circulating human coronaviruses. In contrast, IgG antibodies are generated, and then on secondary infection, they can be reboosted, and subsequent infections don't tend to generate any more IgM, but they generate IgG. And so you can see that IgG responses go up, and they stay up in virtually all the population for all these 4 circulating human coronaviruses. So when we looked at this data, and by we, I really mean almost all the work was done by Jenny Levine in the group, what Jenny found was that the mean age of first infection with these 4 coronaviruses is relatively low. If we look at it using IgM, it comes out to be under 4 years. And if we look at IgG, which is probably a more reasonable way to look at it, it would probably be even earlier. So really, individuals get exposed to and infected by coronaviruses very early in life, and thereafter you see signs of immunity being maintained, presumably by reinfection. Okay, so let's see what we can understand so far. The first thing I showed you was that immunity wanes. The second thing we noted was that there was virtually no severe disease. That's because infections of children are mild. We don't know what infections in adults would be like because everyone gets infected when they're children. But there are some signs that when the beta coronaviruses first emerged, for example, there's a suggestion that OC43 first emerged in the 1800s, it did cause severe infection. So it's quite likely that the circulating human coronaviruses, if they entered the population for the first time in a naive population, they would cause more severe disease in adults. But because people are getting infected as children, that immunity seems to protect them. So it seems that there's a relatively high efficacy of immune efficacy against getting disease, which is IEP. And the last bit that Jenny did was that she looked at and this plot is on the right is a little bit complicated, and I'll walk you through it. The colors represent the mean age of first infection. So the brown corresponds to a mean age of first infection being very young, 0 to 1. The purple, a mean age of first infection quite old, over 10 years of age, okay? On the x-axis is what the relative infectivity of secondary infections is, and on the y-axis is how fast immunity wanes after a given infection. How long does it take for a person to get reinfected on average? So 0.5 is about 2 years, which is what the data is sort of vaguely consistent with. So you see, if immunity wanes so that people get infected every 2 years, then to get a mean age of first infection of between 3 and 5 years, which is the white sort of color on this panel, you need a relative infectivity of secondary cases of about between, of somewhere around a quarter or a little bit more. So dependent on what the relative, the rate of waning of sterilizing immunity and what the relative rate infectivity of secondary cases is, you can tell that there is some transmission from secondary infections. So now with this data from endemic human coronaviruses, we can sort of do an experiment, and the experiment is to see what would we expect an epidemic to look like if one of these endemic human coronaviruses was to emerge in the human population.
Just to say that's 15 minutes, Rustom, if that's right.
Okay.
So if you could wrap up in a couple of minutes, that would be ideal, if that's
okay.
right.
So what you see is initially individuals of all ages are infected, and you get a large peak, which is the black line. Individuals of all ages are infected, but over time, infections gradually move to only the low age groups, the young age groups. So now what would you expect this to be for the transition in severity of disease? Well, the transition of severity depends on what the age-dependent severity is. For CoV-1 and CoV-2, it's very mild in kids and only severe in adults. So as we move from the epidemic phase, which is early when everyone gets infected, in the epidemic phase, adults have severe disease. But in the endemic phase, it's only young children getting infected. The average age of first infection is very young. If this induces good protection against pathology on subsequent infections, then over time we see that the relative severity goes down dramatically. And sort of in conclusion over here, what we have is, if we look at what we expect the transition to be, the transition goes from a relatively severe disease, or at least a moderately severe disease for CoV-2, to a mild disease as we move from an epidemic to an endemic state. And that's because we're changing the age of first infection and the generation of immunity. And I'll end over here by quickly saying this sort of conclusion that we're going to go to a relatively mild infection depends on a number of factors and a number of assumptions. One is whether one infection is sufficient to generate protective immunity, whether immunity against pathology wanes over time. It doesn't take into account yet virus variants. And really, it has a relatively simple model for waning immunity, where first immunity provides long-term protection against pathology. And really what we are moving to just now is a more nuanced approach where immunity gradually wanes over time. And that's my last slide, so I should end with the acknowledgements. I should begin by saying, really the concepts of immune efficacy, which are over here, were inspired by the framework of vaccine efficacy, which I learned by lots of discussions with Bets Halloran. The work I present here was done almost completely by Jenny Levine, together with Otto Bjornsted, and we acknowledge support from the NIH. Thank you.
Thank you very much. Thanks very much for a fantastic talk. That's really great. So it's now about 1 minute to 5. So if anyone has any questions, we haven't got any questions yet coming in through the Q&A. Okay, so the first one has actually just come in now. So the questioner says, so it's a bit of a sort of discussion point, but the question is whether we should compare SARS-CoV-2 with measles or with influenza, and what your sort of reflections are on that, please.
Well, clearly we shouldn't compare SARS-CoV-2 to measles, at least that's my view. And indeed, quite a few people had, at least earlier on in the pandemic, did compare it to measles and made lots of comments about eradication and herd immunity. And if we have herd immunity, it's going to be relatively transient. So
yes, yeah. Great. Yeah, agreed. Okay, thanks very much. So I think given the time now, so it's exactly 5 o'clock, I think we should probably wrap up now. So just to say thanks very much to all 3 speakers for absolutely fantastic talks. It was a really interesting session, and I look forward to more talks tomorrow. So I think that tomorrow morning's program begins at 10 a.m. And Claire will correct me if I'm wrong, but I think the first talk, if I remember rightly, is about within host to between host modeling. So one of the things that Julia talked about a little earlier on. So yeah, thanks very much again to everybody. Thanks for coming along. I look forward to seeing everybody tomorrow. Thanks.